Hi everyone, my name is Scott Kermer. I'm a PhD student at Virginia Tech, and today I'm going to discuss with you how we would find the optimum of a metallurgical process where we don't quite understand the dynamics of the process. So here we have a simulated leaching recovery response surface of cerium from a particular ore. Inputs to the simulation include the acid molarity while leaching as well as the molarity of a leaching additive. And we want to find the optimum of this process, which is here, but we don't quite understand the dynamics. So how would we do that? Well, one approach would be to use the expected improvement algorithm. The expected improvement algorithm works by first testing a set of points in the area, so in this case over the response surface, and recording the values. Here we could see this red point is actually the largest observed value out of this set of points. We would then fit a Gaussian process to all of the observations. The Gaussian process has a predictive mean as well as a predictive variance showing the uncertainty of the fit. We want to find improvement over this red point where we would expect to see some improvement, and the Gaussian process allows us to calculate where we would expect to see improvement. But not only that, we can calculate where we would expect to see the most improvement over this red point, and that's this green point here. We could then test the location at this green point, refit the Gaussian process, and repeat until the algorithm converges on the optimum. Now in testing this on a response surface, you could see we ran an initial design of 8 points, labeled 1 through 8. Then we let the expected improvement algorithm take over. And it tests all these points, and at point 13 converges to the optimum. However, this was run on a noisy response surface, so there's going to be some variation in the results. What would be the average behavior? So in order to test that, I ran a Monte Carlo experiment, optimizing this response surface 100 times, and found the mean. On average, it converged to the optimum in 17.38 tests. You could think of them as 17.38 lab experiments. 91% of the trials found the optimum in less than 27 experiments. So that's quite good for this two-dimensional space with noise. And it's a complicated response surface with two optimums, one global optimum. That in itself shows that this proof of concept can be a promising method for optimization of real processes where we don't quite understand the dynamics. Thank you for your time.